Hi, today we're going to take a look at solving systems of equations using the graphing method. This is part of Chapter 9, Section 6 in our McGraw-Hill series. So first of all, we have to understand, what are systems of equations? A system of equations are a set of two or more equations containing the same variables. Now, in this case, we would be talking about bivariate data. And what that means is that we have two different variables. Typically, we are going to be using the x and the y variable. That way, it makes it easier to graph. However, certain word problems or certain situations may cause us to use different variables, such as t for time or c for cost. And that's okay too, as long as we recognize which one is the dependent variable and which one is the independent variable, meaning independent variable going on the x-axis, dependent variable going on the y-axis. We can solve a system of equations by determining where those two equations are going to intersect. And in this particular lesson, we're going to look at where they intersect when we graph them. Now, there is an algebraic method to this, and we're going to get into that in another video. However, right now we want to focus on how do we graph two different equations and find their intersecting point. Now, the intersecting point is then the solution to the system of equations, meaning it is the value where x and y are equal in both equations. Now, our process is the same as what we've been using with graphing, okay? Typically, we want to make sure that we're in slope-intercept form. We need to be able to identify what is the y-intercept or that b value. And just a reminder, slope-intercept form is where we have y equals some slope m and some y-intercept of b. So y equals mx plus b. That is our y-intercept form that we're looking for. So here's an example. Now, the first thing I want to do is I want to make sure, are these in slope-intercept form? And they are. I know this because the y is all by itself on one side of the equation. The next thing I want to do is I want to identify, is there a distinguishable slope, which for the first equation we have 4, and the y-intercept is going to be -3. Now, what that means is that on the y-axis, this line is going to cross at -3. So I'm going to plot this particular equation. So I'm going to start at the origin. I'm going to move down 3 spaces, and I'm going to plot my first point because that's the y-intercept. Now, the slope is 4, which to me, all right, when the slope is 4, that's 4 over 1, meaning we're going to change the y by 4 and change the x by 1. And I'm going to plot another point there. Now I'm going to do this one more time because it fits on my graph. And I like to have at least 3 points if possible. Now, it doesn't have to happen that way, but I prefer it if I could. Now, I'm going to draw a line to connect my dots. And when I do this, I want to make sure that it is a straight line. And one of the things that's hard with doing this on a computer for me, maybe not for you, but for me, is being able to extend my line. So I got to kind of do it in 2 steps there. Okay. My students would all yell at me right now because I didn't put my arrows. I want to put arrows on both sides of this line just to indicate that it's moving in all directions or in both directions equally and forever. So I'm going to use a different color and I'm going to graph this second point. Use green. So I identify that this has a y-intercept of 3. So it's actually in the opposite direction. I'm going to go up 3. And the slope I notice is -2. Now, a slope of -2 means -2 over 1, or down 2, right 1. And you'll notice that it actually links up already. That first point that I drew off the axis is going to link up with the other equation. So I'm going to continue to plot my points. And I'm going to draw my line. So we want to be as concrete as possible here. Okay. And let's put our arrows. So what we found is that there is an intersecting point right here at 1, 1. All right. So our solution, okay, solve the systems by graphing. The solution to all this would be 1, 1. Now, what does that mean? Well, it means that's where they intersect. We can see that visually. But at the same time, we could also plug it in. Remember that this is an x value and this is a y value. If I plug a 1 into this first equation, all right, we would have 4 times 1 and then minus 3. And we would expect it to equal y, right? And equaling y would equal 1. So 4 times 1 is 4. 4 minus 3 is 1. It works. And the same thing with the second equation. Negative 2 times 1 is negative 2. And negative 2 plus 3 is also equal to 1. So it works out that it's the solution set for both equations to be true. Okay? So that's the general idea of a system of equations. Now, sometimes we are going to have a situation like this, and this is our second example. In this example, we notice that our first equation is in slope-intercept form. And I'm going to graph it. So it tells me to have a y-intercept of negative 3 and a slope of 3. So that means up 3 over 1, up 3 over 1. And I can't move down either. So I'm going to draw my line now. About there. And let's not forget our arrows. Let's be good mathematicians and disciplined. However, I'm going to come to this second equation now. This is a problem. I can't graph this yet. What I need to do is I need to solve it for y. So I build a wall. I'm going to use my identity property. X minus x is 0, and 0 plus 2y is 2y. I subtracted y on the other side, or subtracted x on the other side. So I'm going to write this as negative x plus 8. Then I need y by itself. So I'm going to divide all things by 2. So that now y is going to equal negative 1 half x plus 4. So what I did is I solved it for y. That put it into slope y-intercept form. And now I can graph this. So I'm going to start at 4 on the y-intercept. So here's my 4. And my slope is negative 1 over 2. What that means is negative 1, down 1 and right 2. So down 1, right 2. And there it is. It works out nicely for us here. Crossed already. So I'm going to draw my line to complete this process here. And let's always include our arrows. I know. You guys are going to get sick of me saying that. That's the last time I'll say it, I promise. I hope. And I'm going to circle this because that is our solution. So what this is this is the point of intersection. Again, this problem was slightly more complicated because I needed to actually solve for y to get the y-intercept. But when I graph them together, I notice that the intersecting point is right here at 2, 3. So my solution here is 2, 3, and that is just the ordered pair for this particular point. Okay, so again, that's just one of those problems where we're able to find the solution by graphing. However, we needed to do a little bit of work ahead of time. But what happens if, well, let's go over this first. So the bottom line is we solve systems by graphing. All right, so graph the line just like you would any other line using slope-intercept form, and then find the point where they intersect. That's it. That is the solution. Now, in the back of your mind, I know some of you are having a question, and you're saying, wait a second. What happens if the lines are parallel? I know you read my mind, right? What if the lines are parallel and they never intersect? What would be the answer to that system of equations? And it's very simple. If they never intersect, then there's no answer. So what we say is that there's no solution. So when we look at this set of lines that are on the screen, we'll notice that they have the same slope. Now, they cross the y-axis at different places, but the slope is exactly the same. So there is no point in here where they're going to intersect. They're going to go on forever. So we would say that it is no solution. All right. There is no answer. Sometimes we use the shorthand like that, where we can just say no solution. But that is the actual process there. It is no solution. Now, let's look at this example here. Okay. If we had y equals x, this is one of the problems that had come up a little bit ago. And some students were asking about, well, what about y equals x? So here's what we got to do. We have to just graph and look at this as if it were to say plus 0. So we know that this is going to cross at 0, and we know that the slope is going to be 1. So it's actually going to move in this fashion here. So we just can put all these little dots up there. And this is where it's really nice to be able to draw a line, I tell you. So if we back this up and we draw our line, there we go. All right, so there's my line. Now we're going to graph the second one here, which is going to start at 4. Would have helped if I put it into the right context. So let's use the right tool. So we're at 4, and then we're going to go negative 3 over 1. And notice I already crossed. All right, so I'm going to go negative 3 over 1 and plus 3 over 1. And let's graph our line. And it crosses at 1, 1. So again, a very, very, very common question is what happens when we don't have a b value? Well, it's still there. It's just plus 0. And then when we graph these, we find that we do have our solution. So it's going to be at 1, 1. Okay, so just wanted to kind of go over that with you guys. It was just a very simple and quick introduction to systems of equations. We'll review a little bit more in class together, but hopefully this will help set your mind at ease for something that sounds difficult, systems of equations. You'll find that I think it's not that scary. It's not that daunting. It's just graphing lines and looking at where they intersect. See you in class.